Welcome to the course on game theory in the autumn term 2020 at the University Mannheim. This is the first video of week 11. I ask you for your patience. We will come soon in section 6.2 to examples, but before I still want to introduce one more concept in definition 6.11 and discuss this concept in lemma 6.12. So, the two cooperative games AV and AV tilde, so the same player set but possibly different coalition valuations, are called strategically equivalent if there are a positive number k and any real number C1 to Cm such that the coalition valuations are related to one another by the following precise equality. For any coalition B, V tilde of B is equal to k times V of B plus the sum of the constant Ci for I in this coalition B. So this is a precise equality which relates the two coalition valuations. If we know the constants k and C1 to Cm, we can recover V tilde from V and vice versa. So, and if the two coalition valuations are related in this way, then we call the game strategically equivalent and we notate it here with a tilde st. So, and a cooperative game is 0-1 reduced if the coalition value of the total coalition A is equal to 1 and if the coalition values for the player coalitions are all equal to 0. So 0-1 reduced games are obviously essential because 1 is bigger than the sum of zeros. So now the lemma, or part of the lemma, we fix the player set 1 to m, then the set of additive cooperative games is precisely the set of games which are strategically equivalent to the zero game. So the game where the coalition valuation is the zero map. Part B, convexity, subjectivity, essentiality are preserved under strategic equivalence. So if AV is convex, AV tilde is convex. If AV is superadditive, AV tilde is superadditive. If AV is essential, AV tilde is essential, where V and V tilde are so strategic equivalent. So part C, any strategic equivalence class of essential games contains exactly one 0-1 reduced game. So that gives us a normal form, a best representative and a normal form for one strategic equivalence class of games. And the last part, now here we suppose that we have two strategically equivalent games, AV and AV tilde, and with constants k and C1 to Cm with the usual formula. Then I will explain that also the corresponding sets Z of imputations and Z tilde, K of the core and K tilde are closely related, and also the dominance relations are closely related in these two games. That's why we can really consider them as equivalent in some way. So I define an affine linear automorphism, so it's not linear but affine linear. That means I might add constants in each variable from Rm to Rm, called kappa, where vector x goes to kx1 plus c1 until kxm plus cm. So it's k times the original vector x plus the vector of constant c1 to cm. So, and somehow this is the most natural way how to go from the vectors for the first game to vectors for the second game. Then we have that the set of imputations for the tilde game is equal to kappa of the set imputations for the first game, and the core of the second game is the kappa of the core of the first game. And also for any coalition which is not empty, and for any two imputations, we have that imputation x dominates imputation y with respect to b in the first game, if and only if kappa of x dominates kappa of y with respect to b in the second game. So this is all very natural statements, And the proofs are not really difficult, but they take a little bit of time, and now I will go through the proofs. So let me stress, the proofs are not really difficult, but we have to see this as new anyway. So part A said that the additive cooperative games are precisely the games which are strategically equivalent to the zero game, where the collision value is a zero function. So that's first what you have to prove first. Anyway, whenever here we have a game, cooperative game A with collision valuation V, and if you have a positive constant K and arbitrary real constant C1 to Cm, then we can define the new collision valuation V tilde by the usual formula. For any collision B, the V tilde of B is K times V of B plus the sum of these constants Ci for I and B. So then, given V and these constants, we get the strategical equivalent collision valuation V tilde. So now, now suppose in part A that AV is additive. Then I can choose K equal 1, and I can choose this constant Ci equal to minus the collision value of the one-player collision I. Then it turns out that V tilde of is the zero set, the zero function. So that's then the zero map. So namely V tilde of B is then K times V of B. But yeah, V of B here, the V of B here, the V of B here is equal to the sum over I and B of V of I, because this collision valuation is additive, and K is equal to 1, and then I subtract the sum of the Ci, which is Ci is precisely minus V of I, so I get the value 0. So V tilde of B is the value 0 for any collision B, so V tilde is a zero map. And so I've now shown that the original collision valuation and the zero map are strategically equivalent. And one can also go back. Now I suppose that I have a cooperative game which is strategically equivalent to the game with the zero map. Then I know that there exists a positive constant K and arbitrary constant C1 to Cm, such that this value is equal to 0, because by definition of strategic equivalence, this value here is there must be some constant such that this is a V tilde of B, because they are strategically equivalent. So then this is equal to 0. Now I can just make a trivial calculation. I can divide this equality on both sides by, now I can subtract on both sides Ci, the sum of the Ci, and I can divide by Ki, so then I get here this implication. And this tells me that the collision value of the collision B is equal to the sum minus Ci divided by K. And such a sum formula is exactly what we need for an additive cooperative game. So here there's not a deep result. So the additive games are those which are strategically equivalent to the zero map game. So now in part B, we want to show that these conditions of convexity, superadditivity, and essentiality is preserved by strategical equivalence. So suppose we have a convex game AV, and we have this strategical equivalent game with collision valuation V tilde with some constants K and Ci. Then I want to show that V tilde is also convex. Therefore, I could look at this difference, V tilde of the union of two sets, plus V tilde of the intersection, minus V tilde of the first set, minus V tilde of the second set. The sets are called here B and C. So then our formula here tells us that we get K times the collision value V of the union, plus K times Z of intersection, minus K times Z of the first, minus K times Z of the second one. And the sums of these constants, they cancel out, because we have the sum over all the members in the first set and the second set on the left-hand side, and on the right-hand side, those in the union and those in the we have always those in the union, those in the intersection, minus those in the first, minus those in the second, and so this cancels out. So yeah, and then the difference, or the sum which we have here, that is bigger or equal to 0, because the original game was convex and k is positive, so also k times this difference is non-negative. That tells us that this new game with tilde strategic equivalent game is also convex. So this was the most difficult case. For the super additive case, it is easier, and also for the essential case, it's easier. I will not go through those proofs here. Now we come to part C. So part C claims that within one strategic equivalence class of essential games, one has exactly one 0-1 reduced game. So I start with an essential cooperative game, and I want to find constants k and C1 to Cm such that the new game which I construct from this is 0-1 reduced. So then if I look at the total collision, the value of the total collision of the new game is given here. This is v tilde of b of a, and that shall be equal to 1, because v tilde shall be 0-1 reduced. And here we get the value v tilde of the one-player collision, and that shall be 0, because the new game shall be non-0-1 reduced. So these are conditions which we impose. And now the second condition here tells us that, this condition here tells us that Ci is equal to minus k times v of I, where k is in the moment still unknown, but it fixes the constant Ci modulo the constant k. And if we now put this constant Ci here into the first formula, then we get from the first formula the formula here on the lower right side. 1 is equal to k times this difference of the coalition value of the total coalition minus the sum of the coalition values of the one-player coalitions, which is positive because the game is essential. So and now this equality now determines k. So k is fixed and the Ci are fixed, and we see they exist. We have no more conditions. We have conditions which uniquely determine k and the C1 to Cm, but no more conditions. So we arrive at the 0-1 reduced game, and it's unique. So this gives the proof of the part C here. So now I want to erase this mess here. So now I come to part D. For part D, we have to, I want first to see that this affine linear automorphism kappa maps the set of imputations of the first game to the set of imputations of the second game. So a vector x is an imputation in the first game if this condition and this condition here, if both hold. So, and we want to see that they're equivalent to the corresponding conditions for the vector kappa of x for the second collision valuation. So, the sum of the values kappa of x by the definition of kappa of x is equal to the sum here. That's the exclamation mark. It's the definition of our map kappa. And this equality holds if and only this equality holds, because we have the sum of Ci on both sides, which cancels, and here we have the equality here we have just multiplied by k. So the term here and the term here, they differ just by the k which we had. So in this term on the right hand side, I was lazy, you can't read it, but this is equal to v tilde of a here. So the sum of all these values xi is equal to v of a if and only if the sum of the values kappa of x I is equal to v tilde of A. So this is the first condition for an imputation. And the second given is given here. For the original game, the value xi must be bigger or equal to the value of the one-player collision. That's the condition of individual rationality. And it's a similar calculation. Our formula tells us that we have here equality. And then this condition here is equivalent to the condition here, because we have ci on both sides. And then just multiply the inequality by xi by k on both sides. And then again, you can't see the final part. This is equal to v tilde of I. So we have here again that is non-strict inequality here with v tilde of I. So the condition of individual rationality for the original game for some vector xi holds if and only if the condition of individual rationality for the second game holds for the vector kappa of xi. And this tells us that the set of imputations z of the first game is mapped by kappa to the set of imputations of the second game. So now the second line can be generalized easily. We can look at an arbitrary coalition, and then we had this condition for vector in the core, which is given here for the original game. And I want to show that's equivalent to the same conditions for the second game. Here again, you can't see the result. Here they have v tilde of b. And it's again a similar calculation here. This follows from the definition of kappa, and this also follows from the definition of kappa. And here we have the non-strict inequality here for the original game, if and only non-strict inequality holds here. Again, we have the sum of ci for I and b on both sides, and the inequality from the left side is just multiplied by k, which is positive on the right side. So the positivity of k is here important for the preservation of the non-strict inequalities. So this tells us that here the set of the kernel, the core of the first game is mapped by kappa to the core of the second game. So the last statement is the dominance relation. An imputation x dominates an imputation y with respect to b in the first game, if and only kappa of x dominates kappa of y with respect to b in the second game. So, and this is again some similar argument. So we had there this condition of preference. Here, and the condition of effectivity here, and we have to show that they also hold them for the values kappa of x in the second game. So we have seen that this condition is equivalent to this condition just by the same last argument for the games in the core. And we have also seen, we have not seen this with inequality, we have seen this with equality, but it holds also with non-strict inequality for the collision B here. So we have just seen these arguments before. So this tells us that this dominance is preserved in the way we formulated it. So this finishes the proof of this lemma. It's a bit long, but at the end of the day, it's completely elementary. We just need all the time that k is positive, and multiplying an inequality between two real numbers by some positive number preserves this inequality. And adding the same sum of numbers on the left and right side also preserves this inequality. So there's always this thing which we need here in this reasoning here. So this is not a difficult lemma. The section 6.3 and section 6.4 will give more interesting proofs. So in here I want to stop this video. In the next video finally we come to some interesting examples. Thank you very much.